So yesterday we talked about how to find the equation, the slope of the tangent line, which we know is a derivative. And so if you go into any calculus class, if your teacher asks, what is a derivative? You should be able to say, oh, it's the slope of the tangent line, or at least slope. For me, if I hear slope, I'm pretty happy. That will probably be one question on the test is, what is a derivative? And what I'm looking for is the slope of the tangent line. That's all I'm looking for, and that is a really big idea. Well, yesterday we found derivatives by using limits. So the derivative of a function f at a spot A, so at a point A, we can calculate using the limit as x goes to a of f of x minus f of a over x minus a. As you guys saw, that can take like a whole page, and sometimes even more if they get a little bit trickier. Typically in my calculus classes, I make people show the rules using limits and then give you the shortcut. I'm trying out something new, so you guys are kind of lucky. You're not going to have to take a bunch of limits to show it. You'll have one on your test like that. But for the most part, I'm just going to give you the rules and then we're going to try and use them. So we have this notation, f prime of x. We say this is f prime of x. What it is the derivative of f of x. And we have that equal to d over dx of f of x. And what this notation is saying is this first d is the derivative. And then you say of whatever function you're looking at. And then you read this bottom piece with respect and that second x is 2x. So the derivative of f of x with respect to x. And why in the world would we use this notation? Why is it important? Well, when you hit Calc 2, when you hit Calc 3, really Calc 2, it starts and then Calc 3 kind of carries over in differential equations. It's huge. You'll take derivatives with respect to x, with respect to y, with respect to t, z, whatever letter you're working with. And so you'll use this d over dx notation, but it might be like dy over dz or dt over dx. So you kind of have to be able to look at that and know what is it that I took the derivative of and with respect to what. Also, a really helpful notation that is often used is we'll say that f prime of x is equal to y prime. So we just put a prime on our y. And it's just going from function notation to equation notation. All right. So now some things that I give you. The derivative of c with respect to x equals 0 for any constant. So if I take the derivative of a constant, it is just 0. So dx of just like 5 is 0. if we take the derivative number 2, the derivative of x to the n with respect to x, so I'm taking this derivative of this polynomial, and what's happening is this n comes down, and then you subtract 1 off of it. If you want to see the proof, we can go in my office, we can go through the limit proof and show, oh, the limit shows that this is true. That's what I normally did in class. And I'm changing it so you guys don't have to do the proofs. So you take down the exponent, you subtract 1 off the exponent. And so an example is dx of like, let's say x to the 4th is equal, that 4 comes down, so we get 4x, and then we subtract 1 off the exponent, and that becomes 3. So the slope of every tangent line on the curve of x to the 4th is really just 4x cubed, which is really cool. All right. So let's move to example 1. We have find the derivative of the following function. And most people see this and they write down the derivative and they don't think about their notation. So what we're asking, or what I'm asking you to do, is find the slope of all the tangent lines for x squared. So every single one of the tangent lines. Okay, so if I was to write this out using notation, we'd have f prime of x is equal to the derivative of x squared with respect to x and then what happens is that 2 drops down out in front, x, and then we subtract 1 off the exponent. If we were to simplify this, we get 2x to the 1st, which is really just 2x. And it's okay on your test if you're like, oh, we have f of x equals x squared, the derivative is just 2x, and you see it very quickly. Just make sure you're using proper notation, and you're saying that f prime of x is equal to 2x. There's not much work that you can show on these. All right. So I kind of want to go into a little bit more detail. If I was looking at the point 1, 1, and I drew the tangent line from 1, 1. That didn't go right. And I'm saying that the derivative is 2x. Well, I can evaluate the derivative. I could say find the slope of the tangent line to f of x equals x squared when x is equal to 1. Well, we know the slope of the tangent line everywhere is 2x. So if we find the slope of the tangent line at 1, this is f prime at 1, which is equal to 2 times 1, which is just 2. And we can kind of check that. My line is not perfect, but if I look at x equal 1, my slope is if we go up 2 and over 1. I didn't draw my line perfectly well, but you can kind of see it's up 2 and over 1. So that slope of the tangent line was actually 2. All right, there's another rule that I want to tell you guys that a lot of people kind of make mistakes on. It's not down here, nope. Okay. And I'm going to write number 3 right below here. And that is if I take d dx of x to the first power. So if I have just x, what happens is that 1 comes down in front. So I get 1 x to the 1 minus 1, which is really just 1 times x to the 0. Anything raised to the 0 is 1. So we just get 1. So if you take the derivative of something with an x attached, or you just take the derivative of just x, the derivative is just 1. It has a constant slope of 1 everywhere. All right, questions so far? All right. Example 2 says find the derivative of the following functions. And we have f of x equals x to the 4th plus 3x to the negative 1 minus 5. And we have some more useful rules. We have that d of dx of x plus g is really the derivative of f plus the derivative of g. All this is saying is if we have a polynomial, so functions being added together, then we can take the derivative of each piece separately. So if you have a bunch of functions being strung along with pluses, you can take each piece separately. Number 4 is saying the same thing is true with minuses. If I have a derivative and it's of functions that are being subtracted, all you do is take the derivative separately again. So if you have something like A, you just take the derivative of each piece individually. The last rule on here, example number 5, we have d dx of c of f of x. And that c is just a constant. So c is a constant. And when you do that, the constant just sticks around out in front. And that's different than the constant up here. So if it's a constant with no x attached, the derivative 0. If it's a constant and it has an x attached, take the derivative of the x piece like you normally would and multiply by that constant. So for example, if we had the derivative of 3x squared that 2 drops down in front, and we get 2 times 3 x to the 2 minus 1, which is really just 6 to the x to the first power. All right, so any questions about these rules? All right, before I do an example, I'm going to see if you guys can try these. Try A and B. All right, go ahead and get in your group, and talk about how you took this derivative. Maybe you guys showed steps differently. See if you got the same thing. All right, so let's go through these together. I'm going to show way more work than I expect you guys to show on the test. I just want to show you how these rules are being used. So if we're taking the derivative, we get f prime of x and we want the derivative with respect to x of x to the fourth plus 3x to the negative 1 minus 5. Well, that third and fourth rule say if they're being added or subtracted, you can take their derivatives separately. So this is d dx of x to the fourth plus plus d dx of 3x to negative 1 minus d dx of 5. So that's kind of using rule 3 and rule 4, separating them up. Again, showing way more work than I'd expect you guys to show on a test. And then we have that constant on the second term that we have 3x to negative 1. That 3 is a constant. It can be moved out. So I get d dx of x to the fourth plus 3 d dx of x to negative 1 minus d dx of 5. Okay, now I have my derivative surrounding either x's or constants. This first one, that 4 comes down, 4x, and then I subtract 1, plus 3, again, that negative 1 comes down, x, and we subtract 1. However, that 5 has no x's attached to it. So it just goes away. So we get minus 0. That's that rule, that second rule that we talked about on the first page. If it has no x's, it doesn't have a slope. And so simplifying this down, we get 4x cubed minus 3x to negative 2 and minus 0, so that just goes away. Okay, that was a lot of work to be shown. You don't have to do that much work. I am perfectly okay if on the test you tell me that f prime of x is equal to 4x cubed minus 3x to negative 2 plus 0. So if you look at it and you know how to, and you have these rules really down pat, and you're just like, oh, that's the derivative, I'm fine with that. But if you like the steps, then keep up with the steps. All right, any questions about this? You guys are quiet. All right, I'm gonna assume quiet means, actually, I'm not gonna assume. Thumbs up if you feel good, thumbs down if you feel bad. Okay, good. At least I'm getting some feedback. I'll take it. All right, part B. We want to take the derivative here. Again, I'm going to extend this out and I'm going to show you that I'm okay with you just taking the derivative. So f prime. Also, when you take the derivative on the left-hand side, you need to have f prime or y prime. Something prime needs to be on that left-hand side. If you don't, you will get a -1 notation. It's my favorite thing to type on or write on a page. Yes.
You're just gonna have that for our answer then, or for like?
While you're showing your work, you need to show me kind of what you're doing, because a lot of people will write f of x equals this, and it doesn't. It's f prime. So you want to start off with, oh, I'm taking the derivative, and here's what I did. And then when you get to your answer, you can just kind of box it in, but you want to make sure you have it. All right, so we have f prime of x equals 1/2 x cubed, or f of x equals 1/2 x cubed minus x squared plus 100. So this is d dx of 1/2 x cubed minus 3x squared plus 100. We can split this out, and I'm going to go ahead and skip a step to 1/2 d dx of x cubed minus 3d dx of x squared plus d dx of 100. I kind of combined rules 3, 4, and 5 together. All right, now I'm going to take the derivative. Remember that number drops down and we subtract 1. So we get 1/2 times 3, x to the 3 minus 1. This next one, that 2 drops down, so I have negative 3 times 2, x to the 2 minus 1. And this last one doesn't have any x's, and when it doesn't have any x's and you're taking the derivative of it, it goes to 0. So simplifying this, making this a little bit nicer, this is 1.5 x squared minus 6x plus 0. And you can leave off the plus 0. Yes.
Could we leave the 1.5 is 3 over 2?
Yes. Depending on what math class you're in, you're going to see decimals or fractions more. In my class, I'll start off with decimals because my solutions have decimals. And then as we move through the semester, I'll start using fractions more. In Calc 2, you use a lot of fractions. I'm following a lot of Rob's notes, and he loves decimals because he allows calculators. I allow calculators too. I just forget decimals are a thing. So either one's fine. If you take a different math teacher, they're going to want fractions. All right. So any questions about these two? All right. So moving on to example 3, it says evaluate the derivatives of the following functions. Well, if you've probably noticed by now, derivatives are all about the exponents. We bring down one of the exponents, we subtract one off. Bring down an exponent, subtract one off is pretty much what we're doing. That's the pattern. Well, if we have something that looks like a, y equals the square root of 5, we don't really have that exponent isolated or that function isolated. And we don't have a function being added. We have a function composed with another function. So we need to rewrite this. So the first thing I'm going to do is rewrite so that the exponents, we just have one exponent on the x. So y is really equal to x to the 5th raised to the 1/2. If you remember that from back in the college algebra days. Well, we can take this and rewrite this again. And this is y equals x to the 5/2. So 1x being raised to an exponent. All right, now we want to take its derivative. So y prime is equal to d dx of x to the 5/2. And since that's kind of isolated, the 5/2 is going to drop down. And then we need to subtract 1 off the exponent. If you like fractions, leave this in fraction form. If you're not a fan of fractions, feel free to use decimals. Either way, I'm going to bust out my handy dandy calculator. So 5/2 minus 1. If you have the TI-84, feel free to stick with 1.5. But what's really nice is if you hit the math key, it's under that green alpha key, and see where it says frac, you get 3/2. So our answer is 5/2 x to 3/2. In Calc 2, I often get a lot of people like, how did you do 5/2 minus 1? It's like, in my calculator. I'm teaching you guys to do mathematics and not be calculators, is kind of the joke that I always like to say. It's like, if you have a calculator that can do it, then use that. If you prefer the decimal answer, you can have 2.5 x to the 1.5 is our final answer. All right, so any questions about that particular problem? Okay, so part B, I don't want you to write down your answer, but I do want you to think in your head how you might take the derivative of this. If you want to write it off to the side or just think about it, that's okay. I want you guys to think how you might do this using the rules that we have. Okay, does everyone have at least an approach they might think about using? Even if you haven't worked out the derivative? I want you guys to get in a group and see if your approaches are the same. And if you're not, talk about how you think you might do this. What approach might you take?
So I'm just gonna.
Okay, so my guess is you guys got 3 different approaches,
We definitely got different answers as well.
different ways to do that.
Mhm.
Yeah, so one of the most common approaches that people think of, that is wrong, is to take the derivative of the top divided by the derivative of the bottom. That is one way, that is like the most common way that people like, oh, we can do that. But let's look at our rules. so far we only have regular functions and nothing that's being divided. Like, and the x even has to be in the numerator so far. We haven't had anything with fractions in it. So we can't really just take the derivative of the top and divide by the derivative of the bottom. So we need to get this, what I call in kind of a linear form, where all the x's are on top and nothing's being multiplied. So nothing's in a fraction, nothing's being multiplied. So we need to go back to our algebra skills and think of some weird, goofy trick that we can do. All right. So the first weird, goofy trick that I'm going to do is y equals 4 over x cubed minus x over x cubed. It's a little bit goofy, a little weird. Is everyone okay with me taking that leap? I know in Calc 2, I take this leap and people are like, whoa, hold the phone. You can't do that. That is not allowed. So is everyone okay with this? Okay. Where it comes from is if I had like 5x over x squared plus 6 over x squared, I can rewrite that because they have common denominators of 5x plus 6 over x squared. I just went that way. Yeah, I love it in Calc 2 when people are like, nope, that is not allowed. That's illegal. I'm like, nope, we can do it. This is why. All right. So we can break those up. And now we still don't have x's solely in the numerator and just one x per term, right? This first term, our x is in the denominator. We don't know how to take the derivative of that yet. And this one, we have an x in the numerator and the denominator. So we still have that fraction. So let's work this a little bit more. If I have a term in the denominator, how can I move it up to the numerator? Yeah, put a negative in front of the exponent. So I have y equals 4, x to the negative 3. So we move that up. And our second one, we can reduce this. And when we reduce this, we get 1 over x squared. Our x is in the denominator still. So we need to move that one up as well. So we get y equals 4x to the negative 3 minus x to the negative 2. We can officially take the derivative of this using the rules that we've learned. So if you get something that looks wonky and it feels a little hinky, and it's like, I'm not sure we've learned a rule for this, it's probably because we haven't, and you need to use some algebra, fun little algebra tricks and tips to get it into a form so that we can take a derivative. All right. So now actually taking the derivative of this. So y prime is equal to d dx of 4x to the negative 3 minus x to the negative 2. And I'm just going to go ahead and take the derivative of this. If you guys have questions, feel free to ask. That negative 3 comes down, so I have 4 times negative 3, x negative 3 minus 1, so subtract 1 off, minus negative 2, x to the negative 2 minus 1. Multiplying, simplifying, all that fun stuff, we get y prime is equal to negative 12, x to the negative 4, plus 2x to the negative 3. So what questions do you guys have for me? Everybody feel okay with this problem?
So instead of like splitting it apart, could you just like put 4 minus x in parentheses and then move x to the top, adding a negative and then multiply it out?
Yes, you get the same answer that way. I do it this way because people know these exponent rules better than those normally. But if you can see that, go for it. Okay. If you take other people for calculus, as a side note, you might have to simplify one step further. Negative 12 over x to the 4th plus 2 over x cubed. Me, I am fine with this answer above. Not everyone is. All right. So we have this example 4 that says find the derivative of the function, then find g prime of 4 and explain what this tells us. What it's setting us up to do is to be able to find the equation of the tangent line. So we have at 4, we have this line that comes off of it. And if you're not very good at drawing tangent lines, that's okay. Apparently neither am I. So the first thing is find the derivative of the following function. So this is just using our exponent rules. We have g prime of x. That 3 can come down. So I have negative 1.25. Oh, negative 0.125 times 3, x to the 3 minus 2, plus 0.375 times 2, x to the 2 minus 1, and I'm running out of space, plus, now we have something with just an x in it. There's technically a 1 up there, so we can write this as 1.125 times 1, x to the 0, if you really want to. And then we have that constant. We have the negative 0.375. It doesn't have any x's. When you have no x's, you can't find the derivative of it. Or the derivative is just 0. So it's 0. If I simplify this and write this a little bit nicer, I get g prime of x is equal to negative 0.375. I don't know why I wrote a minus 2. That should be minus 1 up here. Squared plus 0.75 x plus 1.125. So x to the 0 just becomes 1. So that is our derivative. On a test, that's about as much work as I'd expect you guys to show. If you show more, I'm happy grading it. If you show less, that's fine too. There's not a lot of work you can show with derivatives. All right, so that's A. Part B says, find g prime of 4 and explain what this tells us. So B, we have g prime of 4. That is equal to negative 0.375, 4 squared, plus 0.75 times 4 plus 1.125. I'm going to bust out my handy dandy calculator. So we have negative 0.375 0.375 times 4 squared plus 0.75 times 4 plus 1.125. And we get negative 1.875. Okay. If I say derivative, your brain should think, yes, we're gonna do that again. If I think derivative, you guys should think, yes. Every day when I taught, last time taught Calc 1, every time after our initial lesson, I walked in, I was like, if I say derivative, you guys say, and they'd scream slope of the tangent line back at me. It just became our thing. So that it's really that important. I even came in Calc 2 because I had those same students again, and I was like, what is a derivative? And luckily they remembered. My silly antics work. Okay, so negative 1.875 is the slope of the tangent line. And in this case, it's a particular slope of the tangent line. It is when x is equal to 4. All right. So that is the slope of the tangent line. I'm going to go a little bit further with this problem because we haven't had any of these notes in here. Yeah, let's find part C. Let's find the equation of the tangent line. So the tangent line is this black line I drew. And we have negative 1.875 as that slope. So down 1.875 over 1. Close to what I drew. And we want a tangent line. Tangent lines are straight lines, right? What's the equation of a straight line typically? Y equals, yeah, mx plus b. What does m stand for? Yeah, so m is slope. And we're looking for the equation of the tangent line. Do we have the slope of the tangent line? Yeah, we found that in part B. So we have y is equal to negative 1.875 x plus b. We only need to find one more variable. We only need to find b. So if we can pick an x and y, we can solve for b. Notice on our graph that we have 1, 1. Oh, hold on. We can't use that point. We have 4 and 2 is what this is. And that 2 isn't exact. It is really close to 2. It's really 2.125, but we're going to use 2. So we're going to get close to the equation of that tangent line. So we're going to plug that in. We get 2 equals negative 1.875 times 4 plus b. If you want to be really exact, you can plug that 4 in and get that 2.125. I'm okay if you use the graph to estimate, but we're going to use our calculator. We have 4 times negative 1.875, and that equals negative 7.5. So we get 2 equals negative 7.5 plus b. I'm going to add 7.5 over. And so I get b is equal to 9.5. All right. So last but not least, putting our equation together, y equals negative 1.875 x plus 9.5. All right. Any questions on that? You could have a test question that asks you to find the equation of a tangent line. And this is how you would go about doing it. I really like this question for a test. It'd be a great test question. Maybe not with all the decimals, but finding the equation of a tangent line. All right. Let's move on to the next lesson. I'm gonna pause it.